Okay, so one special topic, I'll call this kind of, we're using Euclid's algorithm to solve a single type of just one type of example is this, but it's a more law-based one of those longer problems, so that's why we aren't going to do a lot with it. But it's generalized. It's basically what you do. It's like it's like the two big uses of what's done in here, and that's it. Find D equals the GCD of 864,371 and 735,577. Find the GCD of that, and then you also find integers x and y such that, well, this equation is equal to D. This works, fits the equation, and D is the GCD, of course. So 2 parts. First part is just finding it using Euclid's algorithm. So in general, the GCD of AB equals A times X plus BY, which is what this formula is. There should be a Y right there. That's just a mistake. It should be X plus, that times plus 735,577 times Y equals D. So, yeah, linear combination and all that. And of course, you basically do a series of repeated divisions until you get a division with no remainder. You basically remainder equal to 0. So you do several in this case. We have 7 divisions technically we go through here. And we start with 800. Basically, we start with the initial GCD numbers, 864,371, and we divide that by the other number, A and B. Basically, for general, this would be A and this would be B, and you divide, you do B, you divide A by B. Plus 128,794. Basically, that's the remainder from A divides B here. And another time, this divides that remainder of that. You do that several times. Down here, I can try to show this briefly. Basically, another way of thinking of it is you have this division, and it's between 1 and 2 basically. So that means Q equals 1, and whatever's whatever gets you, since these are all positive numbers, it would be whatever gets to 2 basically here. Whatever gets you to 2 is R, like this plus R. 700. Yeah, basically Q plus. Q times, the thing, but whatever. 1 times that plus whatever gets you, plus whatever gets you to 800. Okay, look, I'm trying to overcomplicate this more. Point is that in this illustration down here, Q is equal to, to simplify between the 2 integers, let's say 1 and 2 in this case, it's the lower integer. Basically, it's the generalized form. That's why it's 1 here, because you're not going to fit 2 of these inside of it, inside of that number. The remainder is, of course, R equals A minus QB. So this minus 1 times 735,577, and that's the same here. So divided by, but you bring this down, and I color coded it trying to show how it goes. So 735,577 equals 5 times 128,794. Got a 5. Basically, this divided by that equals 5 point something. So it's 5, and then this is what's the remainder. You have a calculator, so it makes it relatively quick to do at least the division, but you have to do it multiple times and have to remember how to do it ordering. Then you bring down 128,000 something, and then you get equals 1 times 91,607 plus 37,187. Keep on doing it so far and so far. Eventually get to this one, 17,233 equals 6 times 2,721. There's some typos here, but that should be plus 907. The point is that that's going to be the GCD as we see it. We do 2,721 divided by 907. That's 3 times 907. Basically. 3 times 907 gives you exactly 2,721. So the remainder is 0. Therefore, the last non-zero remainder is the greatest common divisor of the two numbers. So yeah, so D equals 907 because that's what GCD is. D equals the GCD of these two numbers. And that's part one. Now the second part is problem is finding X and Y, which it's not that hard if you really know what you're looking at. And it's one of those things where if you were to have notes available to you during an exam or homework, whatever, it would make it a lot easier because you can just copy. You just have to do the method. It's very. There's a couple rules for it that it's nice to be able to reference. But anyway, I hope I explained this well enough. It's not in it's one of the easier algorithms to use, really, especially for this one, the first usage, just generally finding the GCD. It's I'm pretty sure more efficient, especially for large numbers to do this than any other method, really. At least out of the ones we've covered. So I rewrote this thing because this is where the real application of Euclid algorithm is for the factors X and Y in that linear, That's like the big use that's specific to it, pretty much. I have an easier way to find it. So you have a table of this table you form all the time like this, and pretty much all the time A and B go in 0, in the Rn section of where n is 0 and 1. You put your A and B, which is these numbers, and then you put in all the remainders. And except for a remainder of 0. You go so basically all the way up to what the GCD is for remainders. Yep. And I wrote that in pink. Then in brown I wrote the next part. So Qn, the quotient. So these numbers they multiplied. What was the remainder basically? You multiplied this, And when you brought that down, what you multiplied the previous remainders by basically. And you put them in 1 through 7. Yeah. You have as many rows as you have the first two numbers plus the number of remainders. So there's 0 through 7 because there's 0, 1 are A, B, and then 2 through 7 there's 6. Because there's 1, 2, 3, 4, 5, 6. So 6 remainders. So you have 0 through basically your Rn plus 1 amount. Your number of remainders plus 1 basically. Pure numbers from 0 to your number of remainders, one additional columns than what you have remainders. 0, you have. But yeah, so basically the quotients go in 1 through 7 here. There's 7. They're much smaller numbers than most of the. Kind of odd, seem next, but okay. And then finally, your final row is xn, and that's the tricky one. So you basically there's ways to there's statements about calculating these, but the best way is just to remember this method. So 1 is always in this column. It's always going to be in your second to last column, and then the next one right next to it to the left is the negative of this 6 here, so it's negative 6 of the second to last column's Qn row, Qn. So negative 6. Okay, 6, so it becomes negative 6 down here. Then the next ones are all the same method of calculating basically. You do 1 minus 2 times negative 6 because 1 is here, and then 2 times negative 6. Negative 32 is gone here because 1 minus 2 times negative 6 is 30. So negative 32 is negative 6 in this thing minus 2 times 13. See, so for this, you go 2 columns down, and then the next column you do that. The one column that, yeah. I tried to illustrate this. It's kind of hard to even announce and illustrate it. 45. This one, and you do it all the way to the end basically. This is 13 minus 1 times negative 32, so it's 45. Here, negative 32 minus 5 times 45, which is equal to negative 257. Finally, CO2, that's equal to, you have 45 minus 1 times negative 257, so that becomes CO2. And your final, and now that once you have this table filled perfectly, you have your answer. So these are going to be your X and Y values. You basically do sort of cross You go across from each other. There and there. 864,271 basically times x plus that times y here equals 907. So x equals negative 257, y equals 302. That's your answer. And there's one other smaller problem, really short problem, really, that just goes one step further here. Let d be as in problem 3, find one of the solutions in inches of u and v of the equation. So you have u and v here, and you have it equal to 9 times d. Same basic setup there. And we know d already is 907. And we know x and y factors that equal 907. So, yeah, that's why it stayed here. Then basically 9 times every sane will give you 9 times d equals this times 9 times negative 257 plus this times 302 times 9. And then you basically are multiplying the factor that d is multiplied by, your greatest common divisor is multiplied by a factor, and you can multiply x and y by that factor to get the new values for that. That's all that's done here without much math needed. Just a very basic trick. This trick works and you get your answer, and that's all you have to do. And that's it. And that's using Euclid's algorithm for all it's worth. And you can do other problems, but basically these are like the type that would be in